Welcome back to another explainer. Today we're unpacking a foundational math concept that literally pops up everywhere, from basic arithmetic all the way to real-world everyday problem solving. We are talking about the highest common factor, or the HCF. We're going to figure out exactly how to find it, no matter what kind of numbers we're dealing with. Okay, let's dive into this. So here's our roadmap for this explainer. First up, what actually is the HCF? Then we'll build our toolkit by covering 3 distinct methods: listing factors, prime factorization, and the division method. And finally, we'll wrap up with some real-world applications. All right, section 1, what is the HCF? Let's get absolutely clear on this core concept. Simply put, the highest common factor is the largest number that divides 2 or more numbers exactly, leaving 0 remainder. Let's break that down word by word, right? Factor just refers to a number that divides perfectly into another number. Common means it's a factor shared by all the numbers you're looking at. And highest, well, that just means it's the biggest one of the bunch. So put it all together, it is literally the biggest number that fits perfectly into all of your numbers. Now, you've probably heard a bit of an alphabet soup when it comes to these math acronyms, which can get kind of confusing, but here is the absolutely crucial point. HCF, GCD, which stands for greatest common divisor, and GCF, greatest common factor. They all mean the exact same thing. Totally interchangeable. So if you suddenly see GCD on a test, but you only studied HCF, take a breath, don't panic, you already know exactly what to do. Moving right along to method 1 in our toolkit, listing factors. This one is really best for smaller numbers. Let's systematically walk through calculating the HCF of 12 and 18. Step 1, we just write out all the factors of 12. Those are 1, 2, 3, 4, 6, and 12. Step 2, we do the exact same thing for 18. That gives us 1, 2, 3, 6, 9, and 18. For step 3, we're playing a matching game. We look closely at both lists to spot the common factors, the numbers that show up in both rows. We can easily see they share 1, 2, 3, and 6. Finally, step 4, just pick the highest number from that shared list. The highest is 6. Easy, right? When we highlight those shared factors, it brilliantly illustrates exactly why 6 is the winner. It's just the biggest shared number in both lists. But let's be real, writing out every single factor gets pretty exhausting if you're dealing with bigger numbers. And that leads us to method 2, prime factorization. Think of this as your reliable workhorse for numbers of absolutely any size. Let's see how this builds on that 12 and 18 example we just did. If we break 12 down into its primes using a factor tree, we get 2 times 2 times 3. If we do the same for 18, we get 2 times 3 times 3. Now, if we organize these into a Venn diagram to find the HCF, we only actually care about the overlap, the specific prime factors that both numbers share. In this case, they share exactly 1, 2, and 1, 3. We pull out those overlapping primes, multiply them together, so 2 times 3, and boom, we get our HCF of 6. Remember, only the overlap counts. Now, I've got a great little shortcut for you here to save some serious calculation time. When you're looking at prime factors, just take each shared prime the smaller number of times it appears. Since 12 has 2 2s, but 18 only has 1 2, we just use the smaller amount, 1 2. It completely takes the guesswork out of the equation. Okay, let's solidify this by testing it on a new pair, 16 and 24. Step 1. 16 breaks down into 2 times 2 times 2 times 2, so 4 2s. Step 2. 24 breaks down into 2 times 2 times 2 times 3. That's 3 2s and a 3. So what do they actually share? Well, 16 has 4 2s, 24 has 3 2s. The smaller amount is 3 2s. So our shared factors are just those 3 2s. Multiply them together, 2 times 2 times 2, and we get an HCF of 8. Now, you might be wondering, what if I have 3 numbers, like 24, 36, and 60? Well, the beauty is this method scales perfectly. You just follow the exact same rule. Keep only what every single number has. 24 gives us 2 by 2 by 2 by 3. 36 is 2 by 2 by 3 by 3. And 60 is 2 by 2 by 3 by 5. The prime factors shared by all 3 of those, just 2 2s and 1 3. Multiply those out, 2 times 2 times 3, and you get an HCF of 12. All right, method 3, the division method, also widely known as Euclid's method. This is your speed hack for large numbers. This method is absolutely brilliant because, honestly, you never have to list any factors. You literally just keep dividing. When you're staring down massive numbers, factor trees can get huge and incredibly messy. Euclid's method lets us bypass all of that. Let's see how it works. Let's carefully walk through the steps using the numbers 48 and 36. Step 1, you divide the larger number by the smaller one. So 48 divided by 36 is 1, with a remainder of 12. Step 2, you take the previous divisor, which was 36, and divide it by your new remainder, which is 12. 36 divided by 12 equals exactly 3, with a remainder of 0. Step 3, the second your remainder hits 0, you stop. You're done. The last divisor you used, in this case, 12, is your HCF. It is incredibly fast once you get the hang of it. Section 5. Real-world applications. Splitting things into the largest equal groups. We've got the methods, but why do we care? Well, HCF solves totally practical problems anytime you want to divide things into the largest possible equal groups with absolutely nothing left over. Picture this relatable scenario. You're organizing a classroom or a desk. You have exactly 12 red pens and 18 blue pens. How do you make identical bundles using all the pens so that every single bundle has the exact same combination? This is where the aha moment happens. The largest number of identical bundles you can make is simply the HCF of 12 and 18, which we know is 6. Tangibly, that means we create exactly 6 identical bundles. If you take those 12 red pens and divide by 6 bundles, each gets 2 red pens. Take the 18 blue pens, divide by 6, each gets 3 blue pens. You end up with 6 perfectly identical bundles and 0 pens left over. Magic! And there are so many other everyday uses for this stuff. If you're cutting 2 ribbons of different lengths into the longest possible equal pieces without wasting any material, you need the HCF. Setting up a hall and arranging rows of chairs into the biggest equal groups, HCF again. And, of course, mathematically, simplifying fractions is just dividing the top and bottom number by their highest common factor to get to the absolute simplest form. So, we've built our toolkit, listing factors, prime factorization, and that speedy division method. Now I want to challenge you to test this out. Grab a piece of paper. Can you use the division method, Euclid's method, to find the HCF of 56 and 42? I'll give you a quick hint. 56 divided by 42 is 1 with a remainder of 14. If you follow the next step, you'll find the answer is exactly 14. Give it a shot. Thank you so much for joining me for this explainer. Keep practicing those steps, and I'll see you next time.